Welcome to part 2 of logistics growth. Now in the past we've talked about exponential growth. We assume that a population is directly proportional to its population at any given time. And we had this differential equation, dp dt equals k times p. And we solved this. If you need to go back, that's when we solved differentials. Now, that was exponential growth, and our equation would look something like this. It's our exponential growth equation. However, most populations have what we call a carrying capacity. In other words, the population must level off to what's called a limiting number, which we're going to call L. In this situation, the rate of increase, remember it's a rate, so we're talking about a derivative here, is directly proportional to two things, P and L minus P. Now where P is the population and L minus P is our carrying capacity minus that certain population. So we're actually proportional to two terms here. We call this logistics growth. And there's a differential equation that can be modeled with it right here. And what this tells us, this is the rate, again, it's a rate of growth. So it's a derivative, it's a growth rate. But the L minus P, a little bit different from here, tells us that we're going to be reaching a specific number. Now the second derivative, if you notice, we talked about this in our first function, in our first video here. The second derivative, this will tell us where the population is growing the fastest. And we're going to take a look at this in just a few moments. So let's pretend we work for the Fish and Wildlife Department of the United States government. And we're being told that that the population of a fish satisfies this logistics differential equation. Now, we have to translate this for the non-math speaker, of course. All this is telling us is that the growth rate of fish, that the fish population grows at this rate. So they're telling me that that the fish population will grow at this rate for any given P. Now, I want this in this form. dP dt equals kp L minus P. I want to be in this form right here. Now, this is my population growth. This is my logistics differential. But it's not looking like I want it to. So I'm going to have to factor out a couple things. One, I can factor out a P. Two, I want P to be by itself, so what I'm going to do is I'm going to factor out the 1 over 6,000 as well. So I'm going to factor out P over 6,000 right here. And if I do this, our new derivative, dP dt, the change in population over the change in time. See, it's a growth rate. So population over time is going to become the following. If I divide out, remember I'm dividing out the P over 6,000. Ready? Oh, I'm going to get the P here over 6,000. Be very careful. This P is gone, but if I take 3 and divide it by 1 over 6,000, be very careful, I get 18,000 minus P. This right here is our differential that we're going to solve. Now be careful, we already know what L is. L is 18,000. That is our carrying capacity. Now the next question is very simple. It asks, as time goes to infinity, what's the population going to approach? Well, that's what a carrying capacity is. It says no matter what, the most population of fish we'll ever have in that lake is 18,000. And from there I can get the range. Well, I'm starting, that's what this is for right here. I'm starting with an initial value of 4,000 fish. At time equals 0, we have 4,000 fish. So the range of the number of fish is going to go from 4,000 all the way to 18,000. Now notice the 4,000, I'm actually going to make that a hard bracket. That should be hard bracket because this is where we start. We literally start with 4,000 fish. But why is this one soft? Well, because we can only approach it. The population of fish will never reach 18,000, but it will approach it. Remember, this is asymptotic. Asymptotic. There we go. Why I majored in math. It's an asymptote. We'll just leave it at that. There we go. It's an asymptote. I can spell that today. So it'll never reach it. We might get 17,999.5 fish, but we'll never get the 18,000. Math humor. Alright, so for part C, now we get a little bit more into the calculus. It says, for what values is the curve increasing or decreasing? So they're asking us, when is the population growing? That's what we're looking for. Where is the population growing? Right there. So this should sound familiar. It's our first derivative test. So I'm going to take my derivative, dp dt, set that equal to 0. And I'm going to find my critical numbers. We haven't done this in a while, so be careful. So if I go up here, I set each of these factors equal to 0. The first one's easy. When the population is 0, the rate's going to be 0. Hopefully that makes sense. I should not have to explain biology to you, right? No fish, no babies. The second, where the population is going to be 0, is when P equals 18,000, when I reach my carrying capacity, which should make sense also because we can't get above that. At 18,000, they're like, okay, we can't have any more baby fish, so they stop. Now, I'm going to set up my first derivative test, dp dt. Well, that affect the population, and I'll put my critical numbers, 0 and 18,000. Now I'm going to put a special number here too, the 4,000. I put that there because that's where I'm starting. Basically what that means is anything between 0 and 4,000 I'm not really worried about because the population is not going to be there because we're starting at 4,000. I pick a number in between. I might pick 10,000. And by picking 10,000, right, let's see what happens. If I plug 10,000 into the P over here, that's a 0 down there, not a P. That's positive. And if I pick 10,000 here, that's also positive. So that's telling me that the slope is, that's right, positive. So take a look. The slope is never decreasing, which means the population of fish never decreases, never goes down. This says that the population of fish is increasing on the domain, soft brackets, 4,000 to 18,000. And that is because the derivative dp dt is greater than 0. So the population of fish never decreases on that entire interval. Now, part D, where is it curve concave up or concave down? So they're really looking for a point of inflection here. In this case right here, where does the population go from increasing at an increasing rate to increasing at a decreasing rate? So we need our concavity test. Be careful, don't confuse this with the second derivative test. If you need to go back, look at my earlier videos to know the difference between the first derivative, concavity, and the second derivative test. Concavity test, need my second derivative. I'm going to write me the original one. Write the original derivative, keep it in. Don't use the simplified one yet. Don't use this one. Just use the original. Minus P squared over 6,000. And I'm going to take the derivative. D2P dt2. And when I take the derivative, this becomes 3 dp dt minus, be careful, 1 over 3,000 p dp dt. And just like before, I'm going to factor out a couple things. I'm going to factor, they both have a dp dt in common, so I'm going to go ahead and take that out. Again, this is the acceleration of population's growth, right? Because the second derivative is how fast our population's rate is changing, acceleration. I'm going to factor out a dp dt, because they both have in common, and a 1 over 3,000 as well, because that's going to make that a whole number, which I want. And if I write this all out, this is going to become, well, if I take out the dp dt, I'm left with 3, but I'm going to divide that by 1 over 3,000, which becomes 9,000, minus, that just becomes p. When I look at my possible points of inflection, what I'm looking for here, where does this function equal 0? Where basically the only choice I have, p is 9,000. Okay? Now, I'm going to do my concavity test here. Remember, I'm only starting at 4,000. I don't need to worry about the 0. And I'm going to look at 18,000. Now, some of you may be wondering why I didn't look at dp dt when I was looking at my possible points of inflection. Where is dp dt equal to 0? Well, we already have that solved from part A, right? That was 0 and 18,000. No need to reinvent the wheel there. Does it make sense? So I already have where dp dt is 0. So I'm only looking, and we already established zeros between 0 and 4,000 is already out of our domain. So I'm only looking between here. I'm going to plug in where my one possible is at 9,000, and I'm going to plug in values. So I'm going to first let P equal the population. Let's say what's going to happen when the population is at 5,000. Well, at 5,000, now, but before we move on, we got to decide something. dp dt, remember, is always positive. We got that from part C above. That's always going to be positive because up here it's positive between 4,000 and 18,000. dp dt was always positive there. So I don't have to show much work there. So the first term is always going to be positive. I have to look at what happens when I plug the 5,000 into the second one. That's positive, so it's going to be concave up. Same thing here. Let's pick 10,000. At 10,000, dp dt is still positive, but that's going to become now negative, so it's concave down. And what we wind up where this function is concave up on 4,000 to 9,000, and that is because the second derivative is greater than 0. Where's it concave down? From 9,000 to 18,000. And that is because the second derivative is less than 0. Alright, we're almost done with here. Now, do we have a point of inflection? Yes. At P equals 9,000. And that is because the second derivative changes signs. By the way, it's also where the population grows the fastest. Which is kind of weird because if you think about it, right after it grows the fastest, the population's rate slows down. Kind of interesting, isn't that? Ooh. All right, now, let's kind of sketch this. All right, now, we're starting with initial population of 4,000. Our carrying capacity is 18,000, and that's our asymptotic line. When the population, remember, here's time, here's population. When the population reaches 9,000, at some point, there's a POI, which we just established. Between the population being 4,000 and 9,000, we know the graph is concave up. And afterwards, it's going to be concave down. So our graph will look something like this. Now notice, people might have noticed, our points of inflection and all of our values are no longer in terms of time. They're now in terms of the y value, the range, which is kind of interesting for us in terms of logistics. So, kind of neat. Now, if you want to find out what happens when we start off at different populations, go to part 2, and we'll take a look at a few more examples. Okay? Bye-bye.